Hi again, welcome to the next video on the integral calculus. In this video we extend our technique for integration to develop a formal way to calculate areas under a curve in the way that brought the methods of Leibniz and Newton together. This is a very important technique for you to understand. With the trapezoidal rule and the associated approaches, we established a basis for estimating the area between a defined curve and the x-axis by drawing one or more trapezia or other shapes of the curve. By increasing the number of trapezia, we obtained better estimates of the area. Hence, although we did not do this, we could have used a very large number of trapezia and obtained a very close approximation to the actual area under a curve. We can certainly adapt this strategy to achieve our objective. For example, we draw a thin slice from the x-axis to the curve. We label the vertical distance from the axis to the curve as y, label the width of the slice as dx. Now, as the slice becomes infinitely thin, it is essentially a rectangle with area of height times breadth, which is y times dx. The total area we are determining is therefore the sum of all the possible slices under the curve from our starting point, here say x equals 0, to the finishing point, here say x equals 5. If we say the sum of all the slices, sum starting with s, then we can stretch out the s a little bit and it becomes this shape, and then we stretch it out a bit more, it becomes this shape, then we stretch out a little bit more and we have this fairly familiar but unusual shape. So the sum of the infinite number of ultra-thin slices is represented by the integral sign. Here, therefore, we can write the integral sign with a 0 under the bottom of it and the 5 at the top of y times dx to mean the sum of the thin slices of height y and width dx, starting from the bottom value, here 0, and going all the way to the top value, which here is 5. Replacing the y with the actual function as shown, equals 9 minus x minus 2 all squared, then we get this statement. We now do our anti-differentiation and, using the rules for definite integrals outlined in the previous video, we obtain our answer. So we do our integration and have our square brackets with 0 and 5 at the end. Then we substitute the 5 in, so it's 9 times 5 minus 5 minus 3 all cubed over 3. And then in brackets minus, now we substitute the 0 in for x and we get 9 times 0, which is 0, minus 0 minus 3, which is minus 3 all cubed over 3. Put that in your calculator and you get 33.33 units squared, which is the area under that curve to the right of the y-axis and above the x-axis. Let's work through another example and we'll find the area under the curve y equals 2x plus 1 from x equals 1 to x equals 4. So step 1, we draw a picture of the curve marking the end points. Step 2, we're going to add a small slice to represent the very thin rectangle. Step 3, we write the area statement to show the sum. So that's going to have the integral sign of y times dx. And then step 4, we're going to replace the y with the x function. So it's now going to be the integral sign of 2x plus 1 dx. Then we place the relevant low and high values on the integral sign. So at the bottom, we're going to put our 1 and our top, we're going to get our 4. We do the definite integral. So we get x squared plus x. And outside of square brackets, we write the 1 and the 4 for the starting and stopping parts. And then we substitute and we find that we get 18 units squared. So then step 7 is simply smile when you obtain your answer, because we've been very careful with our substitution and calculations. Two other comments to make quickly on finding areas under curves using calculus before we leave this video. First of all, when we have linear equations like we had in the previous example, such as y equals 2x plus 1, don't use calculus, use your basic geometry formulas. We can put our verticals at 1 and 4. We've got a trapezium. The area of a trapezium we know how to calculate, so it's just so much easier to do it with the geometry formulas. Similarly, if we have semicircles, like we've got here, then again use your geometry. We know that the area of a circle is pi r squared, so the area of a semicircle is pi r squared over 2, quadrant pi r squared over 4. So here we want to be able to calculate the area below x squared plus y squared equals 4 and above the x-axis. We've defined a semicircle. Now the area of a circle we just talked about is pi r squared, so the area of the semicircle here is pi over 2, and the radius of our circle is 2 square root of 4. So we've got pi times 2 squared over 2, which is 2 pi units squared. Don't use calculus. Use your geometry. Much easier. Second extra point is when we have areas which are below the x-axis. Integration will always calculate these areas as being negative. Hence, when we have to calculate an area, say between a curve and the x-axis, we would need to do separate integrals for areas below the x-axis from those calculations for areas above the x-axis. Then we're going to change the sign of the calculations with negative results because areas cannot be negative. In the case here, I've done the integral, and you can work that through, or I could have just simply used the area of the triangle, half the base times the height. Well, the base is 1 and the height in this case is minus 1. So I'd have 1 times minus 1 all divided by 2, which is minus a half, the same as I get from my integration. For my second triangle, I've got the base 2, the height 2, so 2 times 2 is 4 over 2, which is 2. Now, to be able to get the total area between y equals x minus 1 and the x-axis, I would have to change the minus a half to a plus a half and then add them together. So it's a half plus 2 units, which gives me 2.5 units squared. So nice and straightforward. Using the same example, I want to raise another issue in conclusion. Remember, evil lies in the heart of mathematics teachers. So therefore the question could be asked of you to evaluate the area from 0 to 3 of, under the curve, x minus 1 dx. At first glance, this integral calculates the area between the line y equals x minus 1 and the x-axis, which is exactly what we've just done. But wait, look at the question. Where is the word area? The question does not ask for an area. It just says, do the integral. So therefore, evaluate the integral. As Nike says, just do it. So the integral from 0 to 3, x minus 1, is x squared over 2 minus x from 0 to 3. Fine. Substitute, we get the answer 1.5. It's not 2.5 as we had before because our integral in our area in the right-hand triangle is 2, and now we're going to go 2 minus a half for the first triangle, and so we get the 1.5. Just be careful of that sort of question. Always look, is the word area there or not? Very often it's not. So you should now have the steps to calculate basic areas under curves. Clearly your techniques for anti-differentiation or for integration must be strong. We will extend some of those techniques in a subsequent video. Hope I have helped you to clarify the approach for finding areas. Thanks for watching this video. Hit the like button and subscribe if you haven't already. Also go and do some questions in Test Yourself 1 on my website at drjoesmaths.com. Add a comment below if you have any questions. Good luck. See you later.